Hello and welcome to this Bits of Q series on Template Metaprogramming in C++. My name is Quirijn. Let's get coding. This series will cover all aspects of template metaprogramming, from the very fundamentals to high-performance techniques. But before we get started, I would like to make two assumptions. One, you are already familiar with C++, and two, you have used templates before. It doesn't have to be anything advanced, but just having worked with them a couple of times will make it a lot easier to follow this series. If you haven't used templates before, or are just feeling a bit rusty, I will leave a link in the description for a good introductory tutorial. I recommend watching that first and then going back. Let's get started. So what actually is metaprogramming? To answer that question, let us first look at what programming is. When we program in C++, we write some code that gets turned into an executable by the compiler. Now, when you think about it, an executable is just something that transforms data. For example, it might get some input data from your keyboard or from your file system and turn this into an image on your screen or some audio from your speakers. A metaprogram, on the other hand, is something that transforms programs or code. For example, a metaprogram might look at the structure of another program and based on that create a new program. If you're dealing with a specific situation where a metaprogram looks at its own structure, then we're talking about reflection. C++ template metaprogramming is essentially an application of compile-time reflection. What I mean by that is that we will be writing some C++ code, using templates of course, and we will do this in such a way that during the compilation, our code will look at its own structure, and specifically the types with which it's being called, to steer the compiler into generating the desired executable. Now I realize this all sounds very vague and abstract, so let's look at some examples to make it all a bit more concrete. We are now looking at Compiler Explorer. This is a very nice tool by Matt Godbold, and it allows us to try out different snippets of code, such as this one, with different compilers. We're currently compiling with GCC 11, and we have the C+20 standard enabled. On the right, you see that we have a pane which shows the assembly that's being generated by our compiler, and we have an output pane showing the output of our program. Now, looking at the code, I have made this function print3, which simply takes 3 integers as an input and prints them separated by commas. And indeed, if we call it 1, 2, 3, you see that it outputs 1, 2, 3. Now, say we want to make our print3 function a bit more generic. What we can do is turn it into a template. This will allow us to also use it with strings, doubles, booleans, or any other type. I chose to use different template parameters here for each of the parameters to print3, so we can even mix and match different types. We can now, for example, also add a string. And now we're printing a combination of strings and integers. This is why I like templates so much. They allow you to write generic, reusable code that can be used in any setting. But what if we do not want to treat all our arguments exactly the same? For example, say we want our print3 function to also accept pointers to types, but if the user supplies a pointer, we want it to dereference that pointer and actually output what the pointer is pointing to. If we would try to pass a pointer now, the function simply outputs the address of the pointer. To make our function behave the way we want it, let's first refactor it a bit. I'm now creating a print1 helper function that takes care of the actual outputting of the variables. And then now modifying print3 to use print1 for each of its parameters. So our goal is to dereference our input if it is a pointer. There are different ways to accomplish this, but the way I want to show you right now is through the use of type traits. The standard library provides us with a couple of type traits in the type traits header. In particular, it includes an std isPointer. We can use this isPointer on our template parameter t, and if we do so, the value member will be either true or false, depending on whether t is a pointer type. So what we'll do is we'll make it output the thing t is pointing to if it's a pointer, and otherwise we'll make it output t directly. And as you can see, we now output hello world instead of the address of the hello variable. But what is this isPointer type trait exactly, and how does it work? The best way to explain this is to simply write our own isPointer. As you probably already expected, isPointer is a class template. It is convention to use the value member for type traits, and we'll make this member static so we can access it without creating an instance of isPointer first, and we'll make it const expr so we can use it at compile time. The initial value for the value member will be false. If we were now to remove the std part and use our own isPointer, we'll see the code compiles, but obviously it's no longer correct as our value member is always false. To fix this, we have to create a partial specialization. Depending on your experience with templates, you may not have used specializations or partial specialization before. So, using the power of editing, here's my past self giving a crash course on class template specializations in 3 minutes. Feel free to skip ahead if you already know this part. For this crash course on template specializations, I created a new kind of map, the Q map. Similar to the standard map, it takes two template parameters, a type to use for the key and type to use for the data. This is the definition of the template. One cool thing about my Q map is that I also created some specializations. We have a partial specialization, so this is a specialization where not all the template parameters are filled in, hence partial. This partial specialization works for the cases where our first template parameter is deduced to be an int and works for any possible data type. We also have a full specialization, that is a specialization where all the template parameters are filled in. In our case, it expects two ints, one int for the key, one int for the data type. I can create an instance of the QMap by specifying arguments for each of the template parameters. What happens next is the compiler is going to check all the different specializations as well as the main template definition and see which ones would work for these template parameters. It combines these in what's called the candidate set. In the next step, the compiler figures out which of the candidates is the most specific. This is the implementation that gets chosen. For example, if I create a QMap based off a float and a boolean, it will find that none of the specializations are a good fit because they both expect an int as the key type. As such, it defaults to the template definition. If, however, I use an int and a boolean as template arguments, both the partial specialization as the template definition are a match. Out of these two candidates, the partial specialization is the most specific, hence this is the one the compiler chooses. When I specify two ints, the full specialization, the partial specialization, as well as the original definition are a match. In this case, the full specialization is the most specific, and hence it is chosen. The rules for partial template specialization, and specifically what is meant by a more specific candidate, are quite involved. If you want to know all the details, I recommend reading through this page on CPP reference. For essentially all cases which you come across in practice, however, you can think of this simple definition. A template A is more specialized than template B if the template B can accept all arguments that the template A can accept. And next to that, the template B can accept arguments that the template A cannot accept. In other words, template B accepts arguments that A does not, but not the other way around. As such, A is more specific. Starting in C+17, template class parameters can also be deduced for you. This works as long as there's a way of initializing a class which involves all the template parameters and hence allows for deduction of the types. For example, if you add a constructor which depends on both the key and the data parameter, we can then try to initialize QMap with a float and a boolean, and it will deduce that these are the types to be used for key and data. If we try to do the same for the partial specialization, we get an error, as none of the valid candidates accept an integer and a boolean for its initialization. Other ways of initializing, such as aggregate initialization, can also be used to deduce template parameters. If you want to know all the details, the thing to Google for is class template argument deduction. So, back to our isPointer type trait. We had just created the template definition where we instantiate our value to be false. And now let's create a partial specialization for any pointer to a type T. And here, of course, we will make our value member true. As you can see, the output is now correct again. We output hello world instead of the address of the hello variable. So this is how type traits work. They are class templates that use specialization with a different initial value for their value member to provide you with information about certain properties of your type. In this case, whether your type is a pointer or not. Now, if you think about it, our print1 function behaves differently depending on what type it's being used with, not just the data. What's more, it does not just behave differently, the compiler will actually generate different code because we're using this const expression if statement. Let me show this to you. I'll first simplify the program a bit, because of course, if you don't instantiate a template, it will not end up in a binary. So we'll just use a single print1 call to print a variable a. If you now look at the actual assembly that's being generated, you'll see that the call to print1 now only consists of the actual call to the streaming operator of OStream. Similarly, note that there is no if statement anymore in this binary. There's no conditional jumps in the assembly. If I now change the program to pass a pointer to a, we'll see that some extra instructions are now present to do the referencing. And again, we see that there's only one call to OStream. Now let me demonstrate how this differs from the runtime implementation by simply transforming this function to work at runtime. As you can see, the actual isPointer operation is now being calculated at runtime, and depending on its value, there's a conditional jump, which will either jump over the if part and perform the else, or it will just continue into the if part. This is what we see here, the dereferencing and then the call to the OStream operator, plus a jump that jumps over the else part. If, however, the jump equal triggered, we are in the else part here, and again we have a direct call to OStream. So clearly, the way our function is used actually changes the assembly that gets generated by the compiler. And as such, this is actually our first MetaFunction. So let's quickly undo our changes and we're back. Now, to practice a bit more with these type traits, let's add an extra requirement for our print function. Instead of dereferencing every pointer, we only want to dereference pointers to floating point value. It's not the most realistic requirement, but it'll help me to demonstrate some other techniques. Here again, the type trace header has us covered because it includes an std is floating point. Now, it might make sense to simply do this. Okay, we now again get our address for the string. Let's see if it does dereference floating point types. I'll add a float a and let's make it a double b, and pass their addresses to our print3. So we would expect the address of hello with the actual values of a and b. But instead we get 3 addresses. So clearly this std is floating point is not doing what we think it does. Let's look up its behavior on CPP reference. Okay, we are now on the CPP reference page. And what we see here is that our value will be true if t is of type float, double, or long double, including any CV variants, that's const or volatile variants. Otherwise, it is equal to false. And that makes sense. But in our example, we are not passing it a float or a double. We are actually passing it a pointer to a float or a pointer to a double. That's why it doesn't work. So what we would need here is actually some kind of meta function that would take this t and strip off any pointer if it has one, and then pass it onto its floating point. So let's create an alias here, and we'll call it t without pointer. And what we need now is a meta function to actually strip the pointer of t. Let's just call it strip pointer. We'll pass it our t. And in contrast to our type traits, we don't want to return a value here. We actually want to return a type. Let's see how we can approach this. So we again create a class template. And the convention when returning types from meta functions is to use an alias called type. And By default, we will simply return the type T. Now let's create a partial specialization for when strip pointer is called with a pointer to some type T. And here we'll use as alias type equals T. So this is the T without the pointer. We can now use our strip pointer by simply requesting the type member. And if we then update our isFloating_point to work on T without pointer, we see that it still outputs the address of the string, but for both our float A and double B, it actually does dereference the pointer, just like we wanted. Let's summarize what we discussed today. Metaprogramming is about transforming programs or transforming code. In C++, we can use template specializations to do this. In particular, we looked at two things. First, we looked at type traits and how they can be used to query properties of your types. We then combined this with a const expression if statements to actually choose a different implementation. Secondly, we wrote a MetaFunction to strip a pointer of a type. Now this is really the classic template metaprogramming domain, where both your input and your output is a type. And we'll see in the next episodes that we'll use these building blocks of template specializations to build more complicated MetaFunctions that can actually do computations during the compilation. That's it for this episode. I hope you enjoyed it and learned something new. If you did, make sure to leave a like and consider subscribing to the channel. See you next time.